TPS72000 series LDO linear regulators from Texas Instruments. Welcome to the training module on TI's low dropout voltage regulators. This training module provides a technical review of the TPS72000 family of low dropout voltage regulators and details discussions of internal operation. Dropout voltage is the input-to-output differential voltage at which the circuit ceases to regulate against further reduction in input voltage. This point occurs when the input voltage approaches the output voltage. In the linear region, the series pass element acts like a series resistor. LDO operation can be explained using the NMOS series pass element IV characteristics. It shows two regions of operation, linear and saturation. In the saturation region, the device becomes a voltage-controlled current source. Voltage regulators usually operate in the saturation region. Figure 2 shows the dropout region in relation to the off and regulation regions. Below V dropout, the output voltage drops with decreasing input voltage. The regulator circuit can be partitioned into four functional blocks: the reference, the pass element, the sampling resistor, and the error amplifier. Traditionally, the PNP bipolar transistor has been applied to low dropout applications, primarily because it easily enables a low dropout voltage. However, it has a high quiescent current and low efficiency, which are not ideal in applications where maximizing efficiency is a priority. To have a high efficiency LDO regulator, dropout voltage and quiescent current must be minimized. In addition, the voltage difference between input and output must be minimized since the power dissipation of the LDO regulator accounts for the efficiency. The TPS72000 family of dual-rail, low-dropout linear regulators offers outstanding AC performance like power supply rejection ratio, load and line transient response, while consuming a very low quiescent current of 38 microamps. The TPS72000 supports a novel feature in which the output of the LDO regulates even under light loads when the N pin is left floating. The TPS72000 is stable with ceramic capacitors and uses an advanced BiCMOS fabrication process that yields a dropout voltage of 110 millivolts at 350 milliamp output current. The TPS72000 uses a precision voltage reference and a feedback loop to achieve overall accuracy of 2% over load, line, process, and temperature extremes. At startup, the error amplifier senses the output voltage is low and drives the pass element as hard as possible. The TPS72000 employs an NMOS device as the pass element. The NMOS can have a low dropout voltage with a charge pump. The dropout voltage is determined by saturation voltage across the pass element, and the dropout voltage is proportional to the current flowing through the pass element. At light loads, the dropout voltage is only a few millivolts. At full loads, the typical dropout voltage is 350 millivolts. The TPS72000 internal current limits help protect the regulator during fault conditions. The undervoltage lockout circuit on the bias pin is to keep the output shut off until the internal circuitry is operating properly. The TPS72000 uses innovative circuitry to achieve ultra-wideband and high loop gain, resulting in extremely high power supply rejection ratio. Although an input capacitor is not required for stability on the N pin, it is good analog design practice to connect a 0.1 microfarad to 1.0 microfarad low equivalent series resistance capacitor across the N pin and the input supply near the regulator. This capacitor counteracts reactive input sources and improves transient response, noise rejection, and ripple rejection. The bias pin does not require an input capacitor because it does not source high currents. However, if source impedance is not sufficiently low, a small 0.1 millifarad bypass capacitor is recommended. To decrease the voltage variation resulting from load transient, a big value of output capacitor and a low equivalent series resistance of the capacitor are recommended. The TPS72000 is designed to be stable with standard ceramic capacitors with values of 2.2 millifarads or larger at the output. Power supply rejection ratio is a measure of how well a circuit rejects ripple coming from the input power supply at various frequencies and is very critical in many RF and wireless applications. In an LDO, it is a measure of the output ripple compared to the input ripple over a wide frequency range. 10 Hz to 10 MHz is common and is expressed in decibels. To improve AC performance, such as power supply rejection ratio, output noise, and transient response, it is recommended that the board be designed with separate ground planes for VIN and VOUT, with the ground plane connected only at the ground pin of the device. The TPS72000 family of LDO regulators implement a novel Inrush current limit circuit architecture. The current drawn through the N pin is limited to a finite value. The I Inrush limit charges the output to its final voltage. All the current drawn through VN goes to charge the output capacitance when the load is disconnected. Another consideration is when a load is connected to the output of an LDO. The connected load tries to steer a portion of the current away from Vout. The TPS72000 Inrush current limit circuit employs a new technique that supplies not only the I Inrush, but also the additional current needed by the load. As with any regulator, increasing the size of the output capacitor reduces over and undershoot magnitude, but increases the duration of the transient response. The transient response is a function of the output capacitor value, the equivalent series resistance of the output capacitor, the bypass capacitor, and the maximum load current. The application determines how low this value should be. To decrease voltage variation resulting from a load transient, a big value of output capacitor and a low ESR of the capacitor are recommended. The TPS72000 supports a novel feature in which the output of the LDO regulates under light loads when the N pin is left floating. Under normal conditions, when the N pin is connected to a power source, the bias pin draws only tens of milliamperes. However, when the N pin is floating, an innovative circuit is used that allows a maximum current of 500 microamps to be drawn by the load through the bias pin while maintaining the output in regulation. This feature is particularly useful in power-saving applications where a DC to DC converter connected to the input pin is disabled, but the LDO is required to regulate the output voltage to a light load. The figure shows an application example where a microcontroller is not turned off in order to maintain the internal state of memory, but where the regulated supply, shown as the TPS62000, is turned off to reduce power. In this case, the TPS72000 bias pin provides sufficient load current to maintain a regulated voltage to the microcontroller. The internal protection circuitry of the TPS72000 has been designed to protect against overload conditions. It was not intended to replace proper heat sinking. Thermal protection disables the output when the junction temperature rises to approximately 120 degrees C, allowing the device to cool. When the junction temperature cools to approximately 140 degrees C, the output circuitry is again enabled. Depending on power dissipation, thermal resistance, and ambient temperature, the thermal protection may cycle on and off. This cycling limits the dissipation of the regulator, protecting it from damage as a result of overheating. For reliable operation, junction temperature should be limited to 125 degrees C maximum. Most LDO regulators specify a junction temperature to assure their operation. The maximum junction temperature allowable without damage to the device is also specified. This restriction limits the power dissipation that the regulator can handle in any given application. To ensure that the junction temperature is within acceptable limits, calculate the maximum allowable power dissipation and the actual power dissipation, which must be less than or equal to PD max.